Welcome to lesson 3 of week 8. Today we're going to continue our study of nuclear reactions, nuclear chemistry, and we're going to talk a little bit more about the binding energy that causes these things to work the way they do. And remember, we talked about the mass defect when we took the individual particles of protons plus neutrons plus electrons and you added them all together for oxygen, that it weighed more than oxygen weighs, and that energy was the difference. So when we talk about this, we use a term called an electron volt. There's a little e and a big V. It's an electron volt. The electron volt is the amount of energy of one electron accelerated through 1 volt of electrical potential. It's a very insignificant amount. It's so small, but we have to talk about it in electron volts because the joule, which is the normal metric system of energy, is way too big. 1 joule is equal to 6.2415, so 1 joule is equal to 6.2415 times 10 to the 18th electron volts. Massively, massively bigger. Give you an idea, one single molecule of TNT produces about 35.6 electron volts of energy. And since nuclear radiation reactions produce more than TNT does, we usually express these reactions in mega electron volts. So a mega electron volt would be written like this. A mega electron volt. Now, which equals 10 to the 6th electron volts. So we'll just say that equals 10 to the 6th electron volts. Now, with the formula that we gave you yesterday of E equals mc squared, we get 1 atomic unit, which we call as 1U. 1U equals 931.5 mega electron volts. That's 1 atomic unit, and 1 atomic unit is the equivalent of, it's considered the 1 atomic mass unit. So there's a lot of energy available in 1 atomic mass unit, millions of electron volts per every single atomic unit like that. So if you go to figure 17.5 on page 292, you can see atomic mass numbers and the energy, their binding energy from uranium over to the amount of energy between helium and things like that. And fusion and fission. Fission's when you break something apart, like you take a great big giant atom like uranium with fission and you break it apart and it gives off a certain amount of energy. And fusion is when you take smaller ones and smack them together hard enough that they get close enough that they stick together, like 2 hydrogen atoms sticking together and creating a helium atom. And the binding energy there is fusion, because they fuse together, instead of fission where they fissure and come apart. And fusion has way more energy there than fission does. We'll get a little bit more into that a bit later, but So with the nuclear reactions, we already mentioned that if you added up the 8 protons plus the 8 neutrons plus the 8 electrons, that you ended up with oxygen and some energy. And that's because their individual masses, when they come together, they give up some energy, and that releases some equivalency of mass. And mass and energy are somewhat interchangeable there. Now, the rules with this is that the mass numbers, when you add those together, have to be conserved. And you can see this on the top of page 293, the equation there, 17.4, which is right at the bottom of the first paragraph. You'll see that there's 8 protons, 8 neutrons, plus 8 electrons, and it gives you the 16/8 for the oxygen plus the energy. And here again, right below that, it talks about the rules. The mass number must be conserved. The mass number is adding across the top. When you add across the tops of those, you got the 8 of the ones, 8 ones, and then 8 zeros, that gives you the 16. And you go across the bottom, that gives you those numbers. The mass number has to be conserved, and the nuclear charge, the nuclear number, the atomic number has to be conserved. So the protons didn't change, the mass number across the top didn't change, and but then you get some energy. Now let's talk a little bit about nuclear decay. So we talked a little bit about that and how I was mentioning that carbon-14 had a alpha decay, and I was just remembering from off the top of my head yesterday, and that's not true. It's an alpha decay, or sorry, a beta decay, and we'll talk a little bit about what that does. So when carbon decays and breaks apart, we'll start with alpha. So when alpha breaks apart, it ejects a helium nucleus, and they can tell what's going on when that happens because of those deflection plates that I talked about, where they accelerate it across and they can deflect them where they want to go, and they can tell what the mass is and how fast it's going based upon where it hits on the side plates and things like that. So I'll draw you a picture a little bit of that. So right here we have a block of carbon-14, and we have a little window here. And the reason why we do this window is because we want to just have direction. So some of them might go other ways, but whatever comes out here is going to be that ejected particle. And let's just say, for the sake of whatever this is, whether it was something different, we're not going to say right now it's carbon, but there's just something that's radio decaying. And if it's an alpha particle comes out, they'll have a minus charge and a positive charged plate. And so it comes shooting out of here, and if it's a helium nucleus or an alpha particle, it's going to be positive charged. And that means it's going to be pushed away from the positive, and it's going to be attracted to the negative, and so it's going to come out and do this. And because of the fact that it has a high mass and is moving fairly slow, it might hit right here. And if it's a beta particle, it's traveling a lot faster and so it may go something like this or whatever else. So we're going to call this an alpha particle, and this is going to be a beta particle. And so they're cruising along like that. Now, if it was a gamma particle, it's not a gamma particle, sorry, gamma ray. Gamma ray is electromagnetic wave, and it would not be changed. It would just go shooting right out here, and a gamma ray is denoted with gamma symbol. Now, we're going to do a couple of these beta decays to give you an example of how this works. So, if we have the carbon-14, so we got carbon-14, and we're going to break it apart. and it's going to eject an electron. So what happens is a neutron breaks, and as it breaks, it ejects a negative part, and as it ejects that negative part, that means there in the center there's actually a proton, because it was neutral. When you take a negative part out of it, it leaves it as a neutron or a proton, so it went up one. Now it becomes 14 nitrogen, and it added one of these, and there was an electron that has a -1 here, plus there's going to be some energy. So it actually went up one, so the carbon becomes nitrogen. When you have a beta decay, it goes up one. When you have an alpha decay, it goes down two, and it's in this count. So let's do a bromine one. So we're going to have Br, which is right here, and we're going to have it decay, and it's going to do the same thing. So we're going to do a bromine decay, which would be 82/35. And it is going to decay with the beta decay. So it's going to go, this is going to stay the same. This is going to become one more, and it's going to become krypton. And it's going to eject an electron. So when you add these up, you can see that it's the same. This is 35, that -1 is 35. Those stayed the same, and then there's some energy that comes out as well usually. So the beta decay usually happens when everything's mostly happened and there's just a slightly too many neutrons for it to really be stable. And one of those neutrons wiggling around on there breaks. That's usually when that kind of decay happens. Now, gamma particles, I mentioned that there's some energy with these. Gamma or X-rays usually are emitted whenever there's a beta or an alpha decay. Some kind of that is usually present, not always, but usually. So cobalt-60 cobalt right up here, cobalt-60 is an element that's fairly radioactive, and it's used fairly heavily for cancer treatments because of its radioactivity and the way it decays. And I want you to look on page 295 at the top on table 17.2. So up there we see alpha decay. Cause of reaction is just too heavy. The total count's just too much. There's not enough neutrons, and so boom, it breaks out. And this will cause the atomic number to decrease by 2. The number of the mass decreases by 4 because it took 2 protons and 2 neutrons. The stability increases, and it gives you an example there of CM right here, which is cerium breaking and becoming plutonium and giving off the helium. And then you got beta decay, there's too many neutrons. The actual atomic count goes up by 1, there's no change in the atomic one, and it decreases the count. The upper one, it increases. And then down here on the gamma decay, the nucleus is just as in an excited state. There's no change, no change, no change, and it just gives off gamma rays. So for the assignment for this week is going to be to do example 17.1. it walks you through it, but I want you to do it. I want you to go through the process. I want you to fill it out so that you see that it's going to ask for what type of decay happened. And you have to figure out what type of decay was there, whether it's beta, alpha, or gamma. And make a note that if there's an asterisk, then that means that it has an excited nucleus state, which means there's probably going to be some gamma rays that are going to be there as well. Now, one of the things that's with this is there's other things that can come out as well. You can have neutrinos, which are little teeny particles. There's all kinds of stuff, but these are the main ones: alpha, beta, gamma, and the neutrinos. They are another one that can come out. And as they come out, it's a neutron radiation. Doesn't really affect the things quite so much. As it leaves, plutonium does a lot of this, and etc., where they have these neutrino decays. There's other times where you're going to get some of this type of decay, and you have things like hydrogen 3, which is part of like the tritium and things like that can cause some glowing radiation, because sometimes in the process of the neutrino coming out, it'll also release a photon. And as that photon is released, it gives off light, and so tritium, which is based off of the tritium is the hydrogen 3, then that can do that. And it's considered fairly safe because it's not giving off gamma rays or any of those kinds of things. So that ends the lessons for week 8. Here again, be sure to turn in doing the problem, the example 17.1. Go through all 4 of those processes and turn that in to get credit for week 8. Thank you, and we'll see you for our last week.